When we explore the history of electricity and the scientific ideas that shaped modern technology, Gustav Kirchhoff stands as one of the most influential figures. His contributions are not just important, they form the backbone of nearly all circuit analysis used today. To understand why his laws are so crucial, we must go deep into what electrical circuits are, how scientists struggled before his time, what exactly Kirchhoff proposed, and how those ideas changed engineering, physics, and applied science forever. This first keynote captures the essence of his work. Kirchhoff introduced laws that define the behavior of current and voltage in circuits. But this simple sentence carries enormous depth, insight, and historical weight. Before Kirchhoff, circuits were understood in fragments. Ohm's law existed, yes, but it could only handle the simplest of situations. Engineers could analyze a single battery, a single resistor, and a single line of wire. But once the circuit became more complex, multiple loops, branching paths, interconnected components, traditional ideas failed. Electricity was mysterious and difficult to measure. In the early 1800s, researchers knew that charges flowed, and they knew that energy was involved, but the rules that governed those flows were unclear. Many assumptions were based on intuition, not mathematics. Experiments often led to confusion because circuit behavior did not match expectations. This was the scientific environment in which Kirchhoff emerged. Young, mathematically gifted, and deeply interested in the physics of electricity, he approached the problem differently. Instead of focusing on individual components, Kirchhoff looked at the circuit as a whole system. He understood that electricity follows consistent laws everywhere, not just inside a resistor or a battery. His task was to express those laws in a universal way, a way that applied to any electrical network, regardless of complexity or size. To grasp what he discovered, imagine a circuit filled with resistors, capacitors, junctions, and wires all connected in multiple loops. Modern students solve such circuits easily, but only because they rely on Kirchhoff's laws. Without those laws, calculating what currents flow where becomes impossible. Kirchhoff recognized that electric charge behaves like a perfectly organized system. It never vanishes and never spontaneously appears. In the same way, electrical energy in a circuit also follows strict rules. When voltage rises in one place, it must be fully accounted for by drops elsewhere. From these insights, Kirchhoff developed two foundational principles. Though simple at first glance, they reveal deep truths about electricity. The first principle, which he called a conservation rule, dealt with current, the flow of charge. Kirchhoff understood that if electricity enters a junction, it must leave that junction in equal amounts. This became Kirchhoff's current law KCL, based on the conservation of electric charge. The second principle dealt with voltage, the energy carried by charges. Kirchhoff realized that as charge moves around a closed loop, the total increases and decreases in voltage must balance to zero. This became Kirchhoff's voltage law, KVL, based on energy conservation. These laws were revolutionary because they allowed engineers to analyze circuits in a structured, predictable, and mathematical way. They removed the guesswork. Instead of relying on trial and error experiments, electrical behavior could now be calculated with equations applying universally. But we must go deeper into the essence of this keynote. When we say Kirchhoff introduced fundamental laws, we must appreciate both the conceptual and practical significance. Conceptually, he showed that electricity, though invisible, obeys strict principles similar to mass, momentum, or energy in classical physics. Practically, He gave engineers the tools to solve problems they previously could not. To understand how groundbreaking this was, imagine a river network with many branching paths. If water splits at a fork, we naturally know that the amount of water entering must equal the amount leaving. Kirchhoff applied this same intuitive reasoning to electricity, but with mathematical precision. Before him, researchers knew that current flowed, but they could not express its behavior in a general law. Kirchhoff ended this confusion and provided the rules that electrical engineers still use today. What truly sets Kirchhoff apart is his ability to generalize. His laws do not apply only to resistors, only to simple circuits, or only to specific voltages. They apply everywhere. They work with alternating current SE, direct current DC, inductors, capacitors, integrated circuits, power grids, and even complex radio frequency networks. The universality of his laws became the foundation for future discoveries in electronics, electromagnetism, and communication systems. To appreciate the importance of explaining current behavior, we must explore how misunderstood current once was. Scientists in the early 1800s debated whether electricity was a kind of fluid, a type of wave, a material substance, or something else entirely. Some experiments suggested that current was directional, others seemed to contradict that. Without a solid mathematical framework, assumptions led to mistakes. Engineers struggled to design safe electrical systems because they could not accurately predict how current would divide across different branches of a circuit. This led to failures, inefficiencies, and unpredictable results in early telegraph networks and electrical experiments. Kirchhoff's current law resolved all this confusion. Likewise, the behavior of voltage was also unclear before Kirchhoff. Voltage could be measured with devices like galvanometers, but its relationship to a complete circuit path was not fully understood. Engineers recognized that voltage fell across resistors, but they did not know that these drops always added up to the voltage supplied by the source when moving around any closed loop. Kirchhoff's voltage law captured this idea mathematically and universally. Another important layer to this keynote is that Kirchhoff did more than simply observe. He proved. His work was based on physical laws such as conservation of charge and conservation of energy. These principles were already known in physics, but Kirchhoff was the first to apply them directly to electric circuits. He showed that even though circuit components are separate pieces, the laws governing them are interconnected. His work transformed electricity from a field of experimentation into one of mathematical certainty. In addition to simplifying circuit analysis, Kirchhoff's laws also encouraged a shift in scientific thinking. Researchers began viewing circuits as networks governed by underlying principles rather than as isolated pieces of hardware. This new perspective paved the way for the development of network theory, Maxwell's equations, and eventually the complex circuits found in computers and electronic devices. Kirchhoff helped create the mindset that allowed physics and engineering to evolve into more systematic sciences. Furthermore, explaining how current and voltage behave is essential for safety. Electrical fires, overloads, and failures were common in the early days of electrical experimentation. Without knowledge of how current divides or how voltage distributes, engineers sometimes constructed circuits that overheated or failed unexpectedly. Kirchhoff's laws provided the necessary guidelines for designing stable and safe electrical systems. To understand how influential his laws became, consider the fact that nearly every engineering student in electrical or electronic fields must learn Kirchhoff's laws early in their education. These laws are integrated into textbooks, simulation tools, and engineering software. They are applied in circuit boards, power systems, communications, automation, robotics, digital electronics, and more. In fact, it is impossible to design or understand any electrical system without implicitly or explicitly using Kirchhoff's principles. But let us push deeper into the conceptual significance of the keynote. Kirchhoff explained how current and voltage behave. This phrase captures the heart of electrical science. Current is not just the movement of electrons. It is the measurable flow of electric charge. Voltage is not simply electric pressure. It represents the energy per charge available to drive that flow. Understanding these two quantities is essential for understanding all electrical phenomena. Kirchhoff unified these concepts under simple, elegant rules that apply to every circuit ever built. Another way to interpret Kirchhoff's contribution is to see it as bringing order to disorder. Without laws, electricity appears chaotic. Currents can split unpredictably. Voltages can seem inconsistent. But once we apply Kirchhoff's laws, everything becomes structured and predictable. The behavior of the circuit becomes transparent. Kirchhoff gave the world a framework for making sense of the invisible world of electrical charges. His approach was mathematical, but grounded in physical reality. This combination made his laws durable across centuries of technological advancement. Whether circuits are built on large wooden tables, as in the 19th century, or etched onto microscopic silicon chips, as in the 21st century, Kirchhoff's laws remain unchallenged and essential. As we move deeper into the explanation of this keynote, it becomes essential to understand not only what Kirchhoff's laws state, but also the extraordinary impact they had on scientific thinking, engineering design, and the overall progression of electrical technology. In Part A, we explored how Kirchhoff recognized the underlying patterns of current and voltage. Now, we must expand on why these patterns matter so profoundly and how they shaped every generation of electrical innovation that followed. When Kirchhoff presented his laws in the mid-1800s, he was not simply adding to scientific knowledge. He was redefining the entire method by which circuits were understood and analyzed. Before his work, the behavior of currents and voltages in complex circuits was unpredictable and often misunderstood. After Kirchhoff's work, circuits became predictable, solvable, and transformable into mathematical relationships. This shift marked the beginning of modern circuit theory, the very structure upon which electrical engineering stands today. One of the most striking strengths of Kirchhoff's laws is their universality. They apply in tiny circuits inside smartphones, in the wiring of household appliances, in satellites orbiting Earth, and in massive electrical grids supplying power to millions of people. Regardless of the scale, the laws hold true because they originate from fundamental physical principles: conservation of charge and conservation of energy. These principles are as true in nature as the laws of gravity or motion. Kirchhoff had the insight to apply them directly to electrical networks, creating a system that scientists and engineers still use without modification. To appreciate how transformative this was, consider the importance of conservation laws in physics. They tell us that some quantities like mass, energy, or charge do not spontaneously increase or decrease. Before Kirchhoff applied these principles to circuits, there was no unified way to describe how electricity behaved within a network of components. His laws were the first step toward bringing electrical behavior into the same category as other well-established physical processes. This helped elevate electrical science to a more mature and mathematically disciplined field. In Kirchhoff's current law KCL, he mathematically expressed the idea that electrical charge cannot be created or destroyed at a junction. The significance of this law expands beyond circuits. It reflects a fundamental truth about how nature works. Every electron entering a branching point must go somewhere. None disappear. KCL allows engineers to analyze even the most complicated branching circuits by setting up simple equations that balance currents. These equations reveal how much current flows in each branch, enabling design choices that ensure safety, efficiency, and reliability. Similarly, Kirchhoff's voltage law, KVL, encapsulates the principle that energy is conserved in a closed loop. When moving around a circuit loop, the total electrical energy gained must equal the total energy lost. This principle gives engineers the ability to determine how much voltage drops across each resistor, how much energy is stored in capacitors, and how inductors affect the circuit's overall behavior. Without KVL, designing voltage-regulated systems, stable power supplies, or consistent signal pathways would be nearly impossible. However, Kirchhoff's contribution goes beyond merely writing two equations. His ideas formed the basis for network analysis, a field that allows engineers to break down extremely complex circuits into manageable parts. Network analysis relies heavily on his laws, providing a set of tools for solving multiple interconnected loops, analyzing feedback systems, understanding impedance in AC circuits, and designing filters, oscillators, amplifiers, and communication systems. Every advanced technique in circuit design, including mesh analysis, nodal analysis, and superposition, rests on Kirchhoff's initial insights. When we consider how current and voltage behave in real-world applications, Kirchhoff's laws become even more crucial. For example, in national power grids, engineers must constantly ensure that the amount of current entering a substation equals the amount leaving. Imbalances can cause overloads, voltage drops, or dangerous conditions. KCL forms the basis of load analysis, distribution calculations, and fault detection. Meanwhile, KVL is used to maintain stable voltage levels across transmission lines, transformers, and consumer connections. This ensures that homes and industries receive reliable power without damage to equipment. Without Kirchhoff's foundational work, modern power systems could not be intelligently designed or safely operated. Similarly, in electronic devices, circuit boards contain hundreds or thousands of pathways for current. In microprocessors, billions of transistors operate in tightly packed networks. Understanding how current divides and how voltage distributes is essential to ensuring that each component receives the correct operating conditions. Kirchhoff's laws guide engineers as they design printed circuit boards, PCBs, integrated circuits, and low-power electronics. Even when working on the nanometer scale inside a microchip, the same laws apply, highlighting their timeless relevance. One might wonder why these laws have remained relevant for so long without being replaced or revised. The answer lies in the fact that they stem from universal truths. As long as charge and energy remain conserved in nature, and all experiments confirm that they do, Kirchhoff's laws will remain valid. This has allowed them to endure through every technological revolution: the telegraph, radio, telephony, microelectronics, computers, smartphones, and even renewable energy systems. Another remarkable aspect of Kirchhoff's laws is the clarity they bring to circuit design. Their mathematical simplicity makes them ideal starting points for students learning electronics. Yet they remain powerful enough that experienced engineers use them daily. This combination of simplicity and power is rare in science. Many laws are either too simple to handle complex systems or too complicated for beginners. Kirchhoff achieved the perfect balance, giving the world a toolset that is both accessible and comprehensive. Looking at the historical development of electricity, it becomes clear that Kirchhoff's laws marked a turning point. Before their introduction, most knowledge came from experimental observation. After Kirchhoff's work, engineers began to use predictive modeling. They could build circuits on paper before constructing them in reality, saving time, reducing costs, and preventing failures. This shift from trial and error experimentation to analytical design accelerated innovation in electrical engineering. Consider the early days of telegraph networks, which involved long wires stretching across continents. Engineers needed to understand how signals weakened over distance, how currents divided at junctions, and how voltage drops affected communication. Kirchhoff's laws gave them the mathematical foundation to design efficient networks. Without this breakthrough, global communication systems would have developed much more slowly. In modern times, Kirchhoff's laws continue to guide fields far beyond traditional electrical engineering. They play a critical role in electronic communication, robotics, medical instruments, aerospace navigation, renewable energy systems, and more. Solar panels, for example, must be arranged so that voltage and current conditions match the requirements of inverters and batteries. Kirchhoff's laws help determine optimal configurations. In robotics, power distribution systems rely on KCL and KVL to ensure consistent operation across motors, sensors, controllers, and processors. Even in the age of simulation software, Kirchhoff's laws remain the foundation. Every sophisticated circuit simulator, such as SPICE or MATLAB, uses mathematical solvers that depend directly on Kirchhoff's current and voltage laws. These programs automatically generate equations based on the principles Kirchhoff established, demonstrating how deeply ingrained his work is in modern engineering tools. To further deepen the explanation, we must analyze the philosophical impact of Kirchhoff's contribution. His work exemplified the unity of physical principles. He demonstrated that the invisible world of electrical flow follows the same rules of consistency and conservation that govern all natural processes. This insight helped bridge the gap between classical physics and electrical theory long before Maxwell's equations were formulated. In this sense, Kirchhoff's laws laid the groundwork for the broader unification of electromagnetism. Another philosophical dimension to his work is the idea of predictability. By showing that current and voltage follow strict rules, Kirchhoff helped shift the perception of electricity from something mysterious to something orderly and understandable. This shift empowered scientists to explore deeper aspects of electromagnetic theory with confidence. On an educational level, the study of Kirchhoff's laws teaches critical problem-solving skills. Students learn to think logically, break complex systems into parts, and apply universal rules to reach solutions. These skills extend far beyond electrical engineering. They support analytical thinking in physics, mathematics, computer science, and even economics and network theory. In this way, Kirchhoff's influence extends into multiple disciplines, shaping the way students learn and reason. Another significant point when explaining this keynote is recognizing that Kirchhoff provided not just equations, but a systematic approach. His method encourages setting up equations systematically, identifying loops, defining node voltages, and applying relationships until the system becomes solvable. This structured thinking parallels the approach used in solving many types of scientific and technical problems. Engineers often refer to this as the Kirchhoff mindset, a disciplined way of dissecting complexity using fundamental rules. Finally, it is important to emphasize that Kirchhoff's contribution is not static. Though the laws remain the same, their applications evolve as technology advances. In renewable energy, for example, engineers rely on Kirchhoff's laws to design safer and more efficient battery management systems, energy distribution networks, and grid-connected inverters. In telecommunications, his laws help maintain stable voltage levels essential for signal transmission. In medicine, advanced equipment such as MRI machines and life support systems depend on precisely controlled electrical currents governed by Kirchhoff's principles. One of the most remarkable aspects of Gustav Kirchhoff's work is that it transformed electricity from a field dominated by experimentation into a science governed by predictable rules. This transformation is perfectly captured in the second keynote. His discoveries allowed the accurate calculation of unknown currents and voltages. At first glance, this may seem like a technical achievement restricted to engineering classrooms, but in reality, it represents a fundamental leap in human understanding of natural phenomena. Before Kirchhoff, predicting how electricity would behave in complex circuits was nearly impossible. With his laws, calculating unknown currents and voltages became a systematic, repeatable process. To truly appreciate this, we must explore the scientific context of his time, the challenges engineers faced, the methods Kirchhoff introduced, and the long-term impact on technology, society, and education. In the early 19th century, scientists and inventors were just beginning to understand how electricity behaves. While Ohm's law provided a mathematical relationship between voltage, current, and resistance, it was limited to simple, linear circuits with a single path. In these simple setups, one could calculate the current or voltage if the other quantities were known. However, real-world circuits rarely consist of a single resistor and battery. Even basic telegraph networks included multiple junctions, branches, and loops. Once a circuit became more complex, calculating unknown quantities became extremely challenging. Engineers often relied on intuition, experimentation, or trial and error, which could lead to dangerous mistakes, inefficiencies, or failures. Kirchhoff recognized that the limitations of existing methods stemmed from a lack of universal principles that applied to complex networks. While Ohm had dealt with individual resistors, Kirchhoff extended the logic to interconnected systems. His genius lay not only in recognizing patterns, but in formalizing them mathematically. By doing so, he allowed engineers to move from observation-based problem-solving to calculation-based problem-solving, which is far more reliable and efficient. The core insight behind Kirchhoff's ability to calculate unknown currents and voltages lies in the two laws he formulated: the current law, KCL, and the voltage law, KVL. Kirchhoff's current law ensures that the total current entering a junction equals the total current leaving it, reflecting the conservation of electric charge. Kirchhoff's voltage law ensures that the sum of voltage gains and drops around any closed loop equals zero, reflecting energy conservation. When combined, these two laws provide a complete set of equations to describe virtually any electrical circuit, no matter how complex. Consider a circuit with multiple batteries, resistors, and branching pathways. Without Kirchhoff's laws, predicting the current in a specific branch or the voltage across a particular resistor would be a guessing game. Kirchhoff's approach allows one to set up equations systematically, applying KCL at every junction and KVL around every loop. Once these equations are established, mathematical techniques can solve for all unknown currents and voltages simultaneously. The elegance of this method lies in its universality. The same equations apply whether the circuit is a small electronic gadget or a national electrical grid. The practical implications of being able to calculate unknown currents and voltages cannot be overstated. Engineers can design circuits that function reliably without trial and error. Safety is enhanced because potential overloads, short circuits, or incorrect voltage distributions can be predicted before physical construction. Cost savings are significant, as resources are not wasted on failed designs. Moreover, this ability fosters innovation. Designers can confidently experiment with complex networks, knowing that calculations will provide accurate predictions of performance. Kirchhoff's work also paved the way for mathematical techniques like nodal analysis and mesh analysis, which are now fundamental tools in circuit analysis. These methods rely entirely on the accurate calculation of unknown currents and voltages. Nodal analysis uses KCL to define voltage differences between nodes and solve for unknown node voltages. Mesh analysis uses KVL to define currents in closed loops and solve for unknown branch currents. Both methods, directly derived from Kirchhoff's laws, allow engineers to handle circuits with dozens or even hundreds of components with confidence. To appreciate the revolutionary nature of Kirchhoff's contribution, it helps to consider what engineers faced before his work. Early electrical experiments often produced confusing results because there was no consistent method to account for current division or voltage drops. For example, in a network of multiple resistors connected in parallel and series, currents split in ways that were difficult to predict without precise calculations. Miscalculations could lead to overheating wires, burnt components, or failed communication systems. Kirchhoff's methods turned this uncertainty into a solvable mathematical problem, where every unknown could be calculated reliably. His approach also enabled systematic troubleshooting. When circuits failed, engineers could apply Kirchhoff's laws to determine which branch or component was causing the problem. By comparing calculated voltages and currents with measured values, discrepancies could be identified quickly, making repairs faster and safer. This application of calculation to real-world problems was a significant leap forward in engineering methodology. Another critical aspect of Kirchhoff's ability to calculate unknowns is its impact on theoretical physics and later technologies. With precise methods to determine current and voltage, scientists could verify experimental predictions, test hypotheses, and refine their understanding of electromagnetism. This foundation directly supported later work by James Clerk Maxwell, Heinrich Hertz, and other pioneers in electromagnetic theory. The ability to calculate unknowns also allowed inventors to design early telegraphs, motors, and generators with predictable performance, accelerating the electrification of society. Kirchhoff's contributions also extend into AC alternating current circuits, not just simple DC direct current networks. In AC systems, currents and voltages vary with time, often in complex sinusoidal patterns. Kirchhoff's laws still apply, but engineers must account for impedance, phase angles, and reactive components. The ability to calculate unknown quantities in these systems is critical for power distribution, telecommunications, and signal processing. Every modern electrical appliance, communication device, and industrial system relies on this capacity for precise calculation. Furthermore, Kirchhoff's methods provide the foundation for simulation and computer modeling. Modern circuit simulators, such as SPICE, solve systems of equations based on Kirchhoff's laws. These tools allow designers to calculate every current and voltage in a circuit before physically building it. Without Kirchhoff's framework, such simulations would be impossible. In this way, his work transcends time. Principles discovered in the 19th century continue to underpin cutting-edge 21st century technology. The educational significance is equally profound. Students learning electronics first encounter simple circuits and then progressively more complex networks. The ability to calculate unknown currents and voltages is a cornerstone of the learning process. It teaches logical reasoning, mathematical problem solving, and analytical thinking. These skills are transferable, influencing how students approach problems in physics, engineering, and other scientific disciplines. Kirchhoff's approach also inspired the development of circuit design standards. By providing predictable rules, engineers could standardize components, create electrical codes, and develop industry-wide practices. This standardization is essential for safety, interoperability, and efficiency in modern electrical infrastructure. The ability to calculate unknown currents and voltages underpins these systems, ensuring that components from different manufacturers work together seamlessly. Beyond practical and educational applications, Kirchhoff's discoveries had a broader cultural impact. The era of experimentation and uncertainty in electricity gave way to a new era of precision and control. Society could harness electricity not only for experimental purposes, but for practical, reliable applications. Homes, factories, and cities could be powered safely. Telegraph lines could transmit messages over vast distances. Lighting systems could illuminate streets. In every case, accurate calculations of currents and voltages were fundamental to success. Gustav Kirchhoff's ability to enable the accurate calculation of unknown currents and voltages did more than just solve abstract mathematical problems. It fundamentally changed the way electrical systems were designed, tested, and implemented. The real-world consequences of this capability became evident in countless applications, from the telegraph lines of the 19th century to the highly sophisticated microelectronics of the 21st century. Engineers, scientists, and inventors could finally move from intuition-based trial and error to predictive, calculation-driven design. This shift not only saved time and resources, but also reduced the risk of accidents and failures in complex electrical networks. Before Kirchhoff, electrical experimentation often produced inconsistent or inexplicable results. A circuit with multiple paths for current could behave in ways that seemed chaotic. Currents would divide unevenly, and voltages could drop unpredictably across components. Engineers and experimenters relied heavily on repeated trial and error testing, hoping to stumble upon functional arrangements. Kirchhoff's framework replaced guesswork with a systematic, logical approach. By applying his laws, one could set up a system of equations representing the behavior of currents and voltages throughout a circuit, then solve these equations to find precise values for every unknown. This made it possible to design circuits with confidence, predict performance accurately, and troubleshoot effectively when issues arose. One of the most significant advancements stemming from Kirchhoff's work was the development of network analysis techniques. Nodal analysis, for instance, relies on Kirchhoff's current law to relate currents at junction points and determine unknown voltages at different nodes. Mesh analysis uses Kirchhoff's voltage law to relate voltages around loops and determine unknown branch currents. These methods are taught in virtually every electrical engineering curriculum and are applied extensively in industry. The ability to calculate unknowns in such a structured way enables engineers to tackle circuits of enormous complexity, far beyond what could be understood through observation alone. The ability to predict and calculate currents and voltages also has profound implications for safety. Electrical overloads, shorts, and miswirings were common in early electrical experiments and installations, sometimes resulting in fires, equipment damage, or injury. With Kirchhoff's laws, engineers could determine the expected current through every branch and the voltage across every component before constructing a circuit. This predictive capacity made it possible to identify potential hazards and design protective measures such as fuses, circuit breakers, and voltage regulators. By calculating unknowns in advance, engineers transformed electricity from a dangerous novelty into a manageable, controllable resource. Beyond safety, Kirchhoff's laws enabled efficiency improvements. Electrical devices, from early motors to modern electronics, perform best when currents and voltages are optimized according to design specifications. Accurate calculation of these quantities allows designers to ensure that energy is not wasted as heat or voltage drop, and that devices operate at maximum efficiency. This principle applies to everything from small electronic gadgets to massive power distribution networks, emphasizing how foundational Kirchhoff's discoveries are to modern technology. The ability to calculate unknowns also paved the way for fault detection and troubleshooting. When a circuit fails, engineers can apply Kirchhoff's laws to determine the expected currents and voltages, and then compare them with measured values. Discrepancies reveal which components or branches are malfunctioning. This systematic approach to fault identification would have been impossible without Kirchhoff's method of turning the circuit into a solvable set of equations. In industries such as telecommunications, aerospace, and power distribution, this predictive troubleshooting is essential for reliability and operational continuity. Another key impact of Kirchhoff's work is in the field of alternating current AC circuits. AC systems introduce complexities that do not exist in simple direct current DC circuits, such as reactance, phase shifts, and resonance. Even in these more complex systems, the calculation of unknown currents and voltages remains essential. Engineers apply Kirchhoff's laws in combination with phasor analysis and impedance calculations to predict the behavior of AC circuits. This capability underpins power transmission, radio communication, audio electronics, and countless other technologies that rely on alternating currents. Kirchhoff's discoveries also laid the groundwork for modern computer-aided design (CAD) and simulation software. Programs such as SPICE automatically generate the system of equations for a given circuit using Kirchhoff's laws and solve them to find all unknown currents and voltages. This allows engineers to simulate entire electrical systems before building physical prototypes, saving enormous amounts of time and cost while ensuring functional accuracy. From circuit boards to complex control systems, accurate calculation remains the backbone of design, validating the timeless relevance of Kirchhoff's principles. Educationally, Kirchhoff's framework forms the foundation of engineering instruction. Students learn to apply his laws to solve increasingly complex circuits, starting with simple series and parallel configurations and progressing to multi-loop, multinode networks. This process teaches not only electrical theory but also problem-solving skills, logical reasoning, and the disciplined application of mathematical methods. The ability to calculate unknown currents and voltages in a systematic way is a skill that transcends electrical engineering, fostering analytical thinking applicable in physics, computer science, and many other fields. Kirchhoff's contributions also enabled technological standardization. By providing a reliable method for predicting electrical behavior, engineers could develop consistent standards for component ratings, wiring specifications, and voltage levels. This predictability ensured that devices from different manufacturers could interoperate safely and efficiently. Standardization is essential for modern industrial and consumer applications, from household appliances to industrial machinery and national power grids. Without Kirchhoff's ability to allow accurate calculation of electrical quantities, such harmonization would have been far more difficult to achieve. The philosophical and scientific significance of Kirchhoff's laws should not be overlooked. By enabling precise calculations, Kirchhoff demonstrated that electricity, although invisible and sometimes counterintuitive, obeys predictable, universal rules. This insight reinforced the principle that natural phenomena can be described mathematically, supporting the broader scientific movement toward quantification and modeling. Kirchhoff's work bridged theory and practice, connecting abstract physical laws with practical engineering solutions. One practical example of the power of these calculations is found in early telegraph networks. Telegraph lines often spanned vast distances and included multiple junctions and branches. Engineers needed to predict current flow to ensure messages were transmitted reliably and that batteries were not overloaded. Kirchhoff's methods made it possible to calculate precisely the currents and voltages throughout the network, guaranteeing functionality and efficiency. Similar principles apply in modern telecommunications, where signals travel through complex networks of wires, fibers, and wireless links, all of which require careful voltage and current management. In modern power systems, the ability to calculate unknown currents and voltages is essential for grid stability and load management. Engineers use Kirchhoff's laws to model power flows in transmission lines, predict voltage drops, and prevent overloads. This ensures that electricity reaches homes, businesses, and industries safely and reliably. Renewable energy integration, battery storage, and smart grids all rely on these calculations to optimize performance and prevent failures. Without Kirchhoff's framework, modern electrical grids would lack the precision and control necessary for safe operation. Even in highly advanced electronics, from microprocessors to telecommunications satellites, the principles of accurate calculation remain central. Engineers must determine the current through each transistor, the voltage across capacitors, and the energy consumed by logic gates to ensure proper functionality. Kirchhoff's discoveries allow these calculations to be performed systematically, enabling the development of devices that operate at nanometer scales, with billions of components functioning simultaneously without conflict or failure. The ability to calculate unknowns also supports innovative problem solving. Engineers can experiment with new circuit designs, optimize energy efficiency, and test configurations in software simulations before constructing physical prototypes. This reduces costs, shortens development time, and improves reliability. Innovations in robotics, medical electronics, aerospace systems, and renewable energy all benefit from Kirchhoff's principles, demonstrating the enduring impact of accurate calculation. Kirchhoff's work has also influenced research and experimentation. Scientists designing experiments to study electromagnetism can predict the behavior of currents and voltages in their apparatus, ensuring accurate and reproducible results. This predictability was critical for subsequent discoveries in electromagnetic waves, alternating currents, and the principles underlying modern electronics. In conclusion, the ability to calculate unknown currents and voltages represents one of Kirchhoff's most profound contributions to science and engineering. His discoveries provided a systematic, reliable, and universal framework for analyzing electrical circuits of any complexity. They enhanced safety, efficiency, and reliability in countless applications, from early telegraphs to modern electronics and power systems. They enabled educational development, scientific exploration, technological standardization, and innovative design. By turning uncertainty into precise calculation, Gustav Kirchhoff transformed electricity from a mysterious force into a comprehensible, controllable, and usable resource, fundamentally shaping the modern world. Gustav Kirchhoff's contribution to electrical science is both profound and universal. One of the most remarkable aspects of his work is the sheer breadth of its applicability. Kirchhoff's rules comprising the current law, KCL, and the voltage law, KVL, are not limited to small laboratory circuits or specific experimental setups. They are fundamental principles that govern the behavior of electrical currents and voltages in all circuits, regardless of scale or complexity. From a single resistor connected to a battery to the sprawling electrical grids that power entire countries, these laws remain entirely valid. Understanding why and how Kirchhoff's rules apply universally requires delving into the nature of electricity, the fundamental principles behind his laws, and practical examples illustrating their wide-ranging relevance. At the heart of Kirchhoff's rules is the concept of conservation. KCL is derived from the conservation of electric charge. The total current entering a junction must equal the total current leaving it. KVL, on the other hand, stems from the conservation of energy. The sum of voltage gains and drops around any closed loop must equal zero. These are not arbitrary rules, they are consequences of the fundamental physical laws that govern the universe. Because charge and energy are conserved at all times and in all systems, Kirchhoff's rules apply to every circuit, no matter how simple or complex. In small circuits, such as a series of resistors connected to a single battery, applying Kirchhoff's laws is relatively straightforward. The current is the same at every point in a series circuit, which is a direct application of KCL. The voltage across each resistor adds up to the total voltage supplied by the battery, which is KVL in action. Even in this simple context, Kirchhoff's laws allow accurate calculation of currents through and voltages across each resistor. This ability to predict and analyze behavior is crucial for designing even the simplest electronic devices, from LED circuits to home appliances. The true power of Kirchhoff's rules becomes apparent as circuits grow in complexity. When multiple branches, loops, and junctions are introduced, predicting the behavior of current and voltage by intuition alone becomes nearly impossible. In a parallel circuit, for example, the total current splits among several branches. KCL allows us to determine exactly how much current flows through each path, even if the branches contain different resistances. Similarly, KVL ensures that the voltage drops across components in each loop balance with the voltage supplied by the source. By setting up a system of equations based on these laws, engineers can calculate all unknown quantities, no matter how intricate the network. This principle scales to large electrical grids, which are among the most complex circuits in existence. National and regional power grids consist of generators, transmission lines, transformers, substations, and millions of loads. The currents and voltages at any given point in such a network are influenced by the behavior of countless other components across the grid. Yet Kirchhoff's rules remain perfectly applicable. Each junction in the grid obeys KCL, ensuring that the current entering a substation equals the current leaving it. Each loop, which may involve transmission lines connecting multiple power plants and cities, obeys KVL, ensuring that the total energy supplied is balanced by the energy consumed and lost along the path. The universality of Kirchhoff's laws makes it possible to model, analyze, and control even the largest electrical networks with mathematical precision. Modern tools for power system analysis are based entirely on Kirchhoff's principles. Engineers use techniques such as nodal and mesh analysis to predict voltage levels, current flows, and energy distribution across the grid. When integrating renewable energy sources like solar or wind, Kirchhoff's rules allow accurate calculation of how additional currents affect the overall network. This ensures stability, prevents overloads, and maintains reliable supply to consumers. The same laws that predict current in a small lab circuit also determine the flow of hundreds of thousands of amperes across continental grids. Another reason Kirchhoff's rules are universally applicable is their independence from the type of current. While originally developed in the context of direct current DC, these laws also apply to alternating current AC circuits, including those with complex impedance from capacitors and inductors. In AC systems, voltages and currents vary sinusoidally with time, but the fundamental relationships of charge and energy conservation remain valid. Engineers use phasor analysis alongside Kirchhoff's rules to calculate unknown currents and voltages in AC circuits, ensuring that the principles scale across different types of electrical systems. The universality of Kirchhoff's rules also applies to microelectronics and integrated circuits. Modern chips contain billions of transistors, resistors, and capacitors arranged in highly complex networks. At this microscopic scale, the same laws govern the behavior of current and voltage as in a household electrical grid. KCL ensures that the sum of currents at every node within the chip equals zero, and KVL guarantees that the energy supplied by voltage sources balances with the energy drops across all components. Despite the enormous increase in scale and complexity, the fundamental rules do not change. They remain as valid at the nanoscale as they are at the continental scale. Kirchhoff's rules also enable simulation and predictive modeling. Software like SPICE automatically applies KCL and KVL to calculate currents and voltages in circuits of any complexity. Engineers can simulate circuits before physically building them, whether it's a simple amplifier or an entire electrical distribution network. The ability to predict behavior accurately is only possible because Kirchhoff's rules are universally valid, providing a mathematical framework that works across all circuit types and scales. In addition, the universal applicability of Kirchhoff's laws has significant implications for safety and standardization. By accurately calculating currents and voltages, engineers can design protective devices such as circuit breakers and fuses to prevent overloads in both small circuits and large grids. The same calculations guide the rating of transmission lines, transformers, and household wiring. Because the principles apply universally, safety standards can be consistently implemented worldwide, ensuring reliability and protection across a wide variety of electrical systems. The philosophical significance of this universality is also noteworthy. Kirchhoff's rules demonstrate that electricity, no matter how complex its path, follows predictable natural laws. Whether the system is as simple as a battery connected to a light bulb or as vast as a power grid connecting millions of homes, the same physical principles govern its behavior. This insight underscores the idea that complex systems are built upon simple, fundamental truths. It highlights the power of mathematical modeling in understanding and controlling the natural world. Finally, the universal application of Kirchhoff's rules illustrates the enduring relevance of his work. Over 150 years after their formulation, these principles remain central to both education and practice in electrical engineering. Students learn them early to analyze circuits. Engineers use them daily to design and troubleshoot devices, and power system operators rely on them to manage entire grids. The fact that the same laws govern both small and large circuits highlights the elegance, simplicity, and timelessness of Kirchhoff's discoveries. In conclusion, Kirchhoff's rules truly apply to all circuits, from simple networks to large electrical grids, because they are founded on universal principles of charge and energy conservation. This universality allows engineers and scientists to calculate currents and voltages accurately, predict system behavior, ensure safety, design complex networks, and model electrical systems across scales. From a single resistor to an entire continent's power supply, Kirchhoff's laws remain the foundation of electrical analysis, demonstrating their unmatched relevance, adaptability, and power in the field of electrical engineering. Before Gustav Kirchhoff's groundbreaking discoveries in the mid-19th century, the study and application of electricity were often a matter of trial, error, and intuition. Early engineers and scientists were fascinated by electrical phenomena, yet the behavior of circuits, currents, and voltages was difficult to predict reliably. While basic observations and laws like Ohm's law provided some guidance, they were limited to simple circuits and could not handle the complexities of real-world electrical networks. Engineers faced circuits with multiple branches, junctions, and energy sources, and there was no systematic method for determining how current would flow or how voltage would distribute. As a result, electrical design often involved guesswork, with experimentation and repeated adjustments required to achieve functional circuits. Mistakes could be costly or dangerous, and progress was slow. Kirchhoff's work changed all of this by introducing universal laws that govern the behavior of electrical circuits: the current law, KCL, and the voltage law, KVL. These laws were rooted in fundamental physical principles: the conservation of electric charge and the conservation of energy. By formulating these principles mathematically, Kirchhoff provided a framework that transformed electrical engineering from an art of approximation into a rigorous, precise science. Engineers could now predict exactly how a circuit would behave before building it, eliminating much of the uncertainty that had previously hindered progress. The key to this transformation lies in the systematic nature of Kirchhoff's laws. The current law states that the sum of currents entering a junction equals the sum leaving it. This law provides a predictable rule for understanding how currents divide in complex networks. The voltage law states that the sum of voltage rises and drops around any closed loop equals zero. This provides a clear method for analyzing voltage distribution across multiple components. Together, these laws allow engineers to construct equations that describe every current and voltage in a circuit, no matter how intricate. The introduction of this method replaced guesswork with calculation, ensuring reliable and repeatable results. Before Kirchhoff, designing even moderately complex circuits required laborious experimentation. Engineers often connected batteries, resistors, and wires in different configurations, and measured the resulting currents and voltages to determine if the circuit would function as desired. If the outcome was not satisfactory, they would adjust connections and repeat the process. This trial and error approach was time-consuming and inefficient, and it provided little insight into why a circuit behaved the way it did. Kirchhoff's laws changed this fundamentally. By translating the physical behavior of electricity into mathematical equations, engineers could now analyze circuits theoretically, predicting outcomes with certainty and understanding the principles behind the results. The transformation from guesswork to precision also extended to educational practices. With Kirchhoff's laws, electrical engineering could be taught as a discipline grounded in mathematics and physics. Students learned to apply systematic methods, solve equations, and reason logically about circuit behavior. This created a new generation of engineers who could design complex electrical systems confidently, without relying on trial and error. Over time, this shift established electrical engineering as a formal science, comparable in rigor to other engineering disciplines such as mechanical or civil engineering. Kirchhoff's work also revolutionized industrial applications. Telegraph systems, electric lighting, early motors, and generators all required accurate predictions of current and voltage to function reliably. By applying Kirchhoff's laws, engineers could design circuits that worked as intended on the first attempt, improving efficiency and reducing material costs. This precision was essential for scaling up electrical systems, enabling the construction of power grids, industrial machinery, and communication networks that served large populations. Guesswork would have been inadequate for such large-scale applications, but Kirchhoff's mathematical framework provided a foundation for design at any scale. Another area where Kirchhoff's laws brought precision is fault detection and troubleshooting. When circuits malfunctioned, engineers could use his laws to calculate the expected currents and voltages at various points and compare them with measurements. Deviations from predicted values immediately indicated the location and nature of a fault. This approach replaced the previously haphazard methods of inspection and trial repair, allowing engineers to identify and correct problems quickly and reliably. In this way, Kirchhoff's work not only enabled the creation of precise designs, but also ensured that maintenance and troubleshooting could be carried out systematically. Kirchhoff's influence extended beyond simple circuits to alternating current AC systems, which involve time, varying voltages, and currents. Even in these more complex systems, his principles apply, often combined with Faser analysis and impedance calculations. This demonstrates the adaptability of his laws. They provide precision not only for direct current circuits, but also for the diverse types of electrical networks that power modern society. Engineers designing power grids, audio systems, and communication networks rely on these precise calculations to maintain stability, optimize performance, and prevent failures. The precision introduced by Kirchhoff also enabled the development of circuit simulation and modeling software. Programs like SPICE automatically apply his laws to generate systems of equations and solve for unknown currents and voltages. Designers can now simulate circuits of immense complexity, including integrated circuits containing billions of components, before constructing a physical prototype. This capability, unimaginable before Kirchhoff, exemplifies how his work transformed engineering into a discipline defined by calculation, prediction, and control rather than trial and error. Furthermore, Kirchhoff's approach influenced theoretical advancements in electrical science. By providing reliable methods to calculate currents and voltages, he allowed scientists to test hypotheses and verify theories in electromagnetism with precision. This helped build confidence in electrical measurements, supported the development of Maxwell's equations, and paved the way for the sophisticated electronics we rely on today. Guesswork was replaced by mathematical modeling, enabling engineers and scientists to explore complex systems systematically and advance the field of electrical engineering. Kirchhoff's laws also facilitated standardization in electrical engineering. Accurate predictions of current and voltage allowed engineers to design components with precise ratings, ensuring interoperability and safety. Standard wire gauges, fuse ratings, and voltage levels became possible because engineers could reliably calculate the stresses and loads that circuits would experience. Without Kirchhoff's precise framework, such standardization would have been extremely difficult, and the growth of industrial and consumer electrical systems would have been severely constrained. In summary, Gustav Kirchhoff's work transformed electrical engineering from a field dominated by guesswork into a precise and rigorous science. By introducing universal laws that govern current and voltage, he provided engineers with the tools to predict, design, troubleshoot, and optimize electrical circuits systematically. His contributions established electrical engineering as a formal discipline grounded in mathematics and physics, enabled the development of safe and efficient industrial systems, and laid the foundation for modern electronics, power systems, and communication networks. The ability to replace trial and error with calculation and reasoning represents one of the most profound shifts in the history of technology, demonstrating the lasting significance of Kirchhoff's discoveries. In the 19th century, the invention of the telegraph marked the beginning of a new era in communication, enabling messages to travel across vast distances in a matter of seconds. While this was a remarkable technological achievement, the practical implementation of telegraph networks faced enormous challenges. Telegraph systems consisted of long lines of wires, batteries, switches, and signal relays. Managing the flow of electric current across such extensive networks was extremely complex. Engineers needed to ensure that signals maintained sufficient strength to reach their destinations, that multiple circuits could operate simultaneously without interference, and that the system remained reliable even under heavy usage. Before Kirchhoff's contributions, designing and analyzing such systems relied heavily on intuition, experimentation, and guesswork. Predicting how currents would divide at junctions or how voltages would drop along long transmission lines was largely uncertain, and mistakes could result in signal failure or wasted resources. Gustav Kirchhoff's insights fundamentally transformed this process. By formulating his two fundamental laws, the current law, KCL, and the voltage law, KVL, he provided a systematic and universal framework to analyze electrical networks. These laws allowed engineers to calculate unknown currents and voltages with mathematical precision, regardless of circuit complexity. In practical terms, this meant that telegraph engineers could design networks with multiple branches, loops, and relay stations. confident that each segment would function as intended. No longer was the performance of a telegraph system left to chance. It could be predicted, optimized, and controlled. The current law, KCL, which states that the total current entering a junction equals the total current leaving it, was particularly valuable for telegraph networks. In these systems, multiple telegraph lines often converged at junction boxes, switchboards, or relay stations. KCL provided a reliable method to determine how much current would flow through each branch of the network. This ensured that signals were evenly distributed, preventing overloads in some lines and weak signals in others. Before Kirchhoff, engineers had little way to predict these distributions, often leading to uneven performance or system failures. With KCL, the flow of current through complex branching networks could be calculated accurately, allowing engineers to design networks that were both efficient and robust. Similarly, Kirchhoff's voltage law, KVL, which states that the sum of voltage gains and drops around any closed loop is zero, allowed telegraph engineers to manage voltage distribution across long lines. Telegraph signals often needed to travel many miles, encountering resistance in wires, batteries, and relay contacts along the way. By applying KVL, engineers could calculate the voltage drops at various points in the circuit and ensure that sufficient voltage remained to activate distant relays and sounders. This capability was critical for maintaining signal integrity, preventing miscommunication, and ensuring that messages arrived correctly at their destinations. KVL provided a predictable framework for designing voltage compensation schemes, battery placement, and line configurations, making long-distance communication reliable. The combination of KCL and KVL also enabled engineers to design parallel and series circuits within telegraph networks. Series circuits ensured that signals traveled sequentially through multiple relays, while parallel circuits allowed multiple messages to travel simultaneously through different branches. Kirchhoff's laws allowed the calculation of currents and voltages in these configurations, ensuring that each branch received adequate power and that signals did not interfere with one another. This capability was essential as telegraph networks expanded to include multiple cities, stations, and relay lines, creating a web of communication that covered entire countries. Beyond telegraphs, Kirchhoff's insights were foundational for the design of early telephone systems, telegraphs with multiplexing, and other communication technologies. As telecommunication networks became more sophisticated, engineers faced increasingly complex circuit arrangements, including crosstalk prevention, line balancing, and signal amplification. Kirchhoff's laws provided a universal analytical tool to handle these complexities, enabling systematic design and optimization. By calculating currents and voltages precisely, engineers could prevent interference, ensure consistent signal strength, and scale communication networks efficiently. Kirchhoff's framework also facilitated the development of mathematical and computational methods to analyze telegraph and communication networks. Techniques such as nodal analysis, mesh analysis, and matrix methods all rely on KCL and KVL. Using these methods, engineers could solve large systems of equations representing complex networks, predicting current flows and voltage drops at every point. This capability was revolutionary, transforming communication system design from trial and error experimentation to precise calculation. It allowed engineers to build large networks with hundreds or thousands of lines, confident in their functionality before any physical installation. The impact of Kirchhoff's insights extended to system reliability and maintenance, telegraph networks required continuous monitoring and repair. By applying Kirchhoff's laws, engineers could calculate the expected currents and voltages throughout the network. When a problem occurred, such as a broken wire, a weak battery, or a malfunctioning relay, comparisons between calculated and measured values allowed engineers to pinpoint faults quickly and accurately. This systematic troubleshooting reduced downtime, prevented costly errors, and improved overall network reliability. Even in the context of long, distance, and international communication, Kirchhoff's laws were indispensable. Telegraph lines spanned continents, crossed oceans via undersea cables, and interconnected multiple relay stations. Each additional branch or relay introduced potential points of voltage drop or current division. Using Kirchhoff's laws, engineers could design these massive systems to ensure signals reached their destinations without loss of clarity or strength. They could calculate the necessary battery placement, resistance compensation, and relay sensitivity to maintain effective communication across thousands of miles. In a broader sense, Kirchhoff's insights represent a turning point in engineering methodology. They exemplify the transition from empirical guesswork to calculation-based precision. Telegraph and communication networks were among the first large-scale applications where this shift was evident. By providing tools to predict system behavior mathematically, Kirchhoff empowered engineers to build increasingly complex networks with confidence, laying the groundwork for modern telecommunications, radio networks, and eventually digital communication systems. Finally, the legacy of Kirchhoff's contributions is evident in modern communication technology. Although telegraphs are now largely historical, the principles he established remain central to the design of electrical circuits, fiber optic networks, satellite communication systems, and computer networks. Accurate calculation of currents and voltages is essential to ensure signal integrity, prevent overloads, and optimize performance in today's high-speed, high-capacity networks. Every reliable communication system, from telegraphs to smartphones, relies on the foundational insights that Kirchhoff provided. In conclusion, Kirchhoff's insights were transformative because they allowed engineers to design complex telegraph and communication systems systematically and reliably. By providing universal laws to calculate currents and voltages in any circuit configuration, he eliminated guesswork, enabled precise network design, ensured signal reliability, and laid the foundation for the expansion of long, distance, and international communication. His work did not merely solve technical problems, it revolutionized the methodology of electrical engineering, establishing the principles that continue to underpin modern communication technology. Gustav Kirchhoff's pioneering work in electrical science laid the foundation for technologies that define the modern world. His principles, the current law, KCL, and the voltage law, KVL, are universal rules that govern the behavior of electrical circuits, enabling precise calculation of currents and voltages in any network. While these laws were formulated in the 19th century, their relevance has only grown as technology has advanced. Today, virtually every aspect of electronics, power distribution, and digital technology relies directly or indirectly on Kirchhoff's insights. Understanding why and how his principles underpin modern systems requires exploring their applications across multiple domains and considering their enduring impact on design, reliability, and innovation. In modern electronics, Kirchhoff's laws are indispensable. Electronic devices ranging from simple circuits in household appliances to the most sophisticated integrated circuits in computers and smartphones depend on predictable current and voltage behavior. Printed circuit boards, PCBs, contain dozens, hundreds, or even thousands of components, all interconnected with conductive pathways. KCL ensures that the current entering a junction divides correctly among all outgoing branches, while KVL guarantees that voltages across loops are balanced according to the energy supplied and consumed. These laws allow engineers to design circuits that function reliably on the first attempt, ensuring that each component receives the correct voltage and current. Without these fundamental principles, modern electronics would be far less predictable, and device reliability would suffer significantly. One clear example is in microprocessors. Modern CPU contain billions of transistors operating at high speed with minimal voltage differences. Kirchhoff's laws govern how current flows through these transistors and how voltage distributes across the chip's internal circuitry. Accurate calculation of these parameters ensures that logic gates operate correctly, data is processed without errors, and heat generation remains within safe limits. The design, simulation, and testing of these components rely heavily on Kirchhoff's framework. Tools such as SPICE automatically apply KCL and KVL to model circuit behavior, allowing engineers to predict performance and optimize designs before manufacturing physical hardware. This precision is a direct extension of Kirchhoff's original insights. In the field of power distribution, Kirchhoff's principles are equally critical. Modern electrical grids are vast, interconnected networks that deliver electricity from power plants to homes, businesses, and industries. These grids include generators, transformers, substations, transmission lines, and millions of endpoints. Ensuring that electrical energy flows efficiently and safely across such networks requires careful analysis of currents and voltages at every node and branch. KCL ensures that the total current entering a substation equals the total current leaving it, preventing overloads and ensuring balance. KVL guarantees that voltage levels around loops remain consistent with energy supplied and losses incurred along transmission lines. Power engineers rely on these calculations to design, operate, and maintain grids, ensuring reliable delivery of electricity on a massive scale. The integration of renewable energy sources like solar panels and wind turbines further demonstrates the reliance on Kirchhoff's principles. These sources introduce variable currents and voltages into the grid, which must be managed to maintain stability. Engineers calculate how these inputs affect overall network currents and voltage levels, allowing for smooth integration of renewable energy without disrupting the balance of supply and demand. In this context, Kirchhoff's laws are critical for maintaining efficiency, preventing power outages, and optimizing energy distribution in a modern, sustainable power system. Kirchhoff's principles also underpin digital technology and communication systems. In digital circuits, voltages represent binary states, high and low signals correspond to ones and zeros. Accurate voltage levels are essential to ensure that these states are interpreted correctly by logic gates, memory cells, and processors. Kirchhoff's laws allow designers to predict voltage drops across resistive, capacitive, and inductive elements, ensuring signal integrity. This predictability is crucial for high-speed data transmission, error-free computation, and the overall reliability of digital devices. Without these principles, digital systems would be prone to malfunction due to unpredictable voltage fluctuations and signal distortions. Modern networked electronics, including the Internet of Things, IoT, smart devices, and large large-scale data centers, also rely on Kirchhoff's laws. In these systems, multiple circuits operate simultaneously, often sharing power supplies and communication lines. KCL allows engineers to calculate how currents divide among different branches, preventing overloads and ensuring that each device receives adequate power. KVL ensures voltage consistency across loops, which is vital for synchronizing operations, maintaining signal levels, and avoiding energy losses. These calculations are performed both in physical design and in simulation tools, providing engineers with confidence that complex networks will function as intended. The relevance of Kirchhoff's principles extends to advanced electronics applications such as robotics, aerospace systems, and medical devices. In robotics, precise control of motors, sensors, and processors requires predictable currents and voltages. Aerospace systems rely on accurate energy distribution to ensure navigation, communication, and safety systems operate reliably. Medical devices, such as imaging equipment and life support systems, demand strict voltage and current regulation to function safely and accurately. In all these domains, Kirchhoff's laws serve as the foundation for design, testing, and operation, ensuring systems are both reliable and safe. Kirchhoff's principles are also integral to educational and engineering practices. Electrical engineering curricula worldwide teach KCL and KVL as foundational concepts. Students learn to apply these laws in theoretical calculations, laboratory experiments, and simulations. This education provides engineers with the tools to design and analyze circuits in any domain, from consumer electronics to industrial power systems. The ability to predict and control electrical behavior based on these universal principles is a skill that bridges generations of engineers, ensuring continuity and advancement in technological innovation. Furthermore, the simulation and modeling of circuits, a cornerstone of modern electronics, would be impossible without Kirchhoff's framework. Software tools automatically generate systems of equations based on KCL and KVL, allowing engineers to solve for unknown currents and voltages in highly complex networks. These simulations reduce development time, minimize errors, and allow for optimization at scales that would be impossible to achieve experimentally. From chip design to grid management, the predictive power of Kirchhoff's laws is embedded in virtually every aspect of modern technology. In conclusion, Gustav Kirchhoff's insights continue to underpin the very foundation of modern technology. Electronics, power distribution, and digital systems all rely on his principles to predict and control the behavior of currents and voltages. From microprocessors and smart devices to national power grids and renewable energy networks, KCL and KVL provide the universal rules that ensure reliability, efficiency, and safety. Kirchhoff transformed electrical engineering into a precise, quantitative science, and the continued dependence of modern technology on his work is a testament to the enduring relevance and power of his contributions. His laws remain as vital today as they were in the 19th century, shaping the design, analysis, and operation of the electrical and digital systems that define contemporary life. More than 150 years after Gustav Kirchhoff formulated his laws, their importance in the study and application of electricity has not diminished. His two fundamental principles, the current law, KCL, and the voltage law, KVL, will form the foundation for understanding how electric currents and voltages behave in circuits of any complexity. These laws are taught to students, applied by engineers, and relied upon by scientists across the globe. Their universality, simplicity, and predictive power make them indispensable tools in both education and practical applications, bridging theoretical knowledge with real-world implementation. At the educational level, Kirchhoff's laws are among the first concepts introduced to students in electrical engineering, physics, and electronics courses. Before encountering these laws, students might understand Ohm's law, which relates voltage, current, and resistance in simple circuits. However, Ohm's law alone is insufficient for analyzing circuits with multiple branches, loops, or power sources. Kirchhoff's laws extend the ability to analyze electrical systems systematically, providing a framework for understanding more complex networks. By learning KCL and KVL, students acquire the skills to calculate unknown currents and voltages in series, parallel, and multi-loop circuits, gaining confidence in their problem-solving abilities. This foundational knowledge is crucial for progressing to more advanced topics, such as AC circuit analysis, network theorems, and digital electronics. KCL, which states that the total current entering a junction equals the total current leaving it, teaches students the principle of conservation of charge in a practical context. When applied to multi-branch circuits, it allows students to determine how currents divide among parallel paths. This skill is essential not only for academic exercises, but also for understanding real-life electrical systems, where current division affects the efficiency, safety, and functionality of devices. By applying KCL in laboratory exercises, students learn to connect theory with experimental observation, reinforcing their understanding of fundamental principles. KVL, which states that the sum of voltage gains and drops around any closed loop equals zero, similarly teaches students the principle of energy conservation. It allows them to calculate voltage drops across components, ensuring that energy supplied by sources is distributed accurately throughout a circuit. Together, KCL and KVL form a complete analytical toolkit for understanding circuit behavior. By mastering these laws, students gain a foundation that can be applied to increasingly complex systems, preparing them for careers in engineering, research, and technology development. For practicing engineers, Kirchhoff's laws are indispensable in designing, analyzing, and troubleshooting electrical and electronic systems. Engineers encounter circuits of varying complexity daily, from small electronic devices to industrial machinery and large-scale power grids. Using Kirchhoff's laws, engineers can calculate the expected current and voltage at any point in a circuit, ensuring proper functionality. This capability allows for the design of efficient, safe, and reliable systems. For example, in power distribution networks, engineers use KCL to ensure that the current entering a substation matches the current leaving it, preventing overloads. KVL is applied to ensure that voltage drops along transmission lines do not compromise the energy delivered to homes and industries. Without these fundamental tools, such precise analysis would be nearly impossible, and modern engineering would revert to trial and error methods. Kirchhoff's laws are also critical in the design of electronic devices. Microprocessors, circuit boards, communication devices, and even consumer electronics rely on precise control of current and voltage. KCL and KVL allow engineers to model complex networks of resistors, capacitors, inductors, and semiconductor devices, predicting how each component will behave under different conditions. This predictive capability is essential for optimizing performance, minimizing energy loss, and preventing component failure. Furthermore, engineers rely on Kirchhoff's laws when designing circuits for high-speed digital applications, ensuring signal integrity and proper timing across intricate interconnections. Scientists, particularly those involved in experimental physics, also rely heavily on Kirchhoff's laws. In research laboratories, accurate control and measurement of electrical currents and voltages are often essential for experiments in electromagnetism, material science, and electronics. Kirchhoff's laws provide a theoretical framework for interpreting experimental results, designing apparatus, and verifying hypotheses. For example, in experiments involving electrical networks or circuits in superconducting or quantum systems, KCL and KVL help ensure that current flows and energy distribution are correctly accounted for, enabling reproducible and meaningful results. Modern simulation and modeling tools are built upon Kirchhoff's principles, further highlighting their importance. Software such as SPICE uses KCL and KVL to calculate currents and voltages in complex circuits, allowing engineers and scientists to simulate performance before constructing physical prototypes. This capability reduces cost, time, and risk while improving reliability. From designing microchips to planning power grids, the universality of Kirchhoff's laws ensures that simulations accurately reflect real-world behavior, bridging the gap between theory and practice. Another dimension of their importance lies in education across the world. Kirchhoff's laws are part of the standard curriculum in schools, colleges, and universities, forming a global foundation for electrical and electronics education. Students in Asia, Europe, the Americas, and Africa all learn to apply these same universal principles, ensuring consistency in training future engineers and scientists. This global adoption reflects the timelessness and universality of Kirchhoff's insights, emphasizing their continued relevance in modern education. The role of Kirchhoff's laws in innovation and technological development cannot be overstated. Every modern communication system, computing device, and industrial electrical network relies on the predictable behavior of circuits that Kirchhoff's laws make possible. Engineers designing new technologies use these laws to test new configurations, optimize performance, and ensure reliability. In robotics, renewable energy systems, electric vehicles, and aerospace applications, the precise calculation of currents and voltages is foundational, demonstrating that Kirchhoff's laws are not just historical tools but active enablers of cutting-edge innovation. Moreover, Kirchhoff's laws instill analytical thinking and problem-solving skills. Applying KCL and KVL requires logical reasoning, systematic analysis, and mathematical proficiency. These cognitive skills extend beyond electrical engineering and are valuable in other scientific and technical disciplines. Students and professionals who master these principles develop a structured approach to solving complex problems, an essential competency in research, design, and technological innovation. In conclusion, Gustav Kirchhoff's laws remain essential tools for students, engineers, and scientists worldwide because they provide a universal, precise, and reliable framework for analyzing electrical circuits. They bridge theory and practice, enabling accurate calculation of currents and voltages, safe and efficient design of devices and networks, and meaningful experimental research. From the classroom to advanced laboratories, from microelectronics to national power grids, Kirchhoff's laws are central to understanding, designing, and innovating in the modern electrical world. Their continued relevance underscores the enduring power of Kirchhoff's insights and their critical role in shaping the electrical and technological landscape of today and the future.